All right, so this is 15.5a video 3, and what we've got is 3 examples to do now that we've kind of know how to do mass and center of mass given a density is included in our surface. And what we're going to focus on is still two-dimensional surface in this one. So let's say that we've got, see, our problem says find the mass, the center of mass of density rho. And our equation that we're going to be given is x squared plus y squared equals r squared. Actually, no, I take that back. We're going to end up using that, so you don't have to erase it if you don't want to. I'm actually giving us the graph here. That does not look great, but we are told that that's negative r, that's positive r. So from that, we can deem that this is a semicircle. It's definitely not drawn to scale. A semicircle with a radius of r, which is where the formula x squared plus y squared equals r squared came from. And it is just the top half of the circle. So we're going to solve this for y, because we do want to put this into a function of x. So solving that for y, you would subtract x squared and then take the square root. So you would get r squared minus x squared underneath your square root. We only need the positive part because it is the top half. All right, so let's find, first of all, to find the mass. Mass is going to be volume times density. Mass equals volume times density. But this is a two-dimensional surface, so really, in this case, it's going to be the area times the density. Well, the area of a semicircle is going to be 1/2 of pi r squared times the density. So there's your mass. And if you can do that because you have a two-dimensional figure, which is a geometric shape that you know easily, there's no need to go through an entire integration process or anything like that. You can do it very easily. To find center of mass, we need to find x bar and y bar. So x bar, remember, is the moment of y divided by the mass. Or you could write that as 1/m times the moment of y. Same thing. Well, we know that the mass is 1/2 pi r squared rho. So it'll be 1/1/2 pi r squared rho. Excuse me. The moment of y is going to be the integral. Let's see, we have to take this thing and integrate it from left to right. So that's going to be from negative r to r, because these are functions of x, of, now remember, even though it's the moment of y, we're doing the x bar part. So it's the x's times the f of x's. So x times the function of x, r squared minus x squared dx. All right, in order to go ahead and, oh, forgot the row. Don't forget the row. But the nice thing is the rows will cancel out. Those are going to go away. So we are going to have to do a little bit of a u substitution here. So u is going to be r squared minus x squared. Du will be negative 2x dx. Remember, r is a constant. It's just the radius. So dx is going to be du over negative 2x. So let's see what we get. So let's see, the 1/2 I can pull up to the top as a 2. So that's going to be 2 over pi r squared integral, excuse me again, of x square root of u times the new dx, which is du over negative 2x. And I'm going to go ahead and change the bounds here. Oh, this is actually kind of nice. So if I plug negative r in for x, I get 0. If I plug r in for x, I also get 0. I really don't even have to finish this one because now I've got an integral from 0 to 0, which just means it's 0. And really, if you think about it, that should make sense. We just found the moment of y, which is where the center of this thing would be to keep it from revolving around the y-axis. Well, if I had drawn it better, you would clearly see that because it is a circle or semicircle centered at the origin, that the center of mass, because it's a constant density, would have to be right at the origin. Now, it isn't going to work that way for the moment of x or y bar because it's definitely not equal from the x-axis up to the top. There is definitely more mass towards the bottom, so you're going to have an actual center of mass for the y bar part to be up the y-axis somewhere, but this part should make sense. The 0 here should make sense. All right, so now let's go ahead because we're actually say that again. We will actually have to do some work past this point, I think, for y bar to figure it out. So y bar, so this one worked out nicely. Y bar is going to be the moment of x divided by the mass, which again is the same thing as 1 over the mass times the moment of x, which is 1 over the mass. Now the moment of x, that one's a little bit different. Oops. Shouldn't have written 1 over mass. I'm going to write that as 1 over 1/2 pi r squared rho. So now that's going to be the integral. Still goes from negative r to r. But remember, this one is rho times 1/2 f of x squared this time, right? But f of x was the square root. So when I square the square root, I'm just going to end up with r squared minus x squared dx. So let's simplify. The rows are going to cancel out. So technically I have a 1/2 on the top and a 1/2 on the bottom. Those are also going to cancel out. It's kind of nice. So now I have to deal with 1 over pi r squared integral from negative r to r of r squared minus x squared dx. So this one's a much simpler antiderivative. Remember, we're doing this with respect to x. It'll be 1 over pi r squared. So it'll be x r squared minus 1/3 x cubed. And we'll evaluate from negative r to r. Okay, let's see what we get. 1 over pi r squared. Plugging in r, I'm going to get r cubed minus 1/3 r cubed minus, plugging in negative r, we're going to get negative r cubed. And then that's going to end up being plus 1/3 r cubed. So within the parentheses here, I'm going to get r cubed minus 1/3 r cubed, which is 2/3 r cubed, minus a negative 2/3 r cubed. So it's really going to give me 4/3 r cubed. So we get 1 over pi r squared times 4/3 r cubed. Which, if you multiply that out, the r cubed is going to cancel out 2 of the r squareds from the bottom. So it looks like I'm going to get 4r over 3 pi. We simplify that all the way down. So there is your y bar. So after all of that, x bar, y bar is going to be 0, 4r over 3 pi. So again, depending on what r is, if you have a semicircle centered at the origin, the top half of the semicircle, it will be based upon the radius. It's going to be 4 times the radius divided by 3 pi, and the x bar part will always be at 0. All right. Let's go ahead and look at example 2. We want to find the centroid if the surface is bounded by cosine of x, y equals 0, x equals 0, and pi halves. All right, so let's take a look at that one. What does that look like? Well, x equals 0, y equals 0 puts this thing into the first octant, or first quadrant, excuse me. Y equals cosine of x, and x equals pi halves. So cosine starts up here at 1, comes down to 0 at pi halves. So that looks like that's the space that we're trying to do. So this is y equals cosine of x. This is pi halves. Of course, x equals 0 and y equals 0. So the centroid, I don't know. We could guess. I'm going to guess it's going to be somewhere in that range right there. I have no clue. It could be more central. It could be more down towards the origin. I'm not really sure. I'm just guessing because it seems like there's more space towards the upper right-hand corner than there is to the lower right-hand corner. So maybe there's going to be more mass up that way. Let's find out. Okay, so the mass. Okay, now this is not a simple geometric shape that we can just take the area of, so we actually have to do some work here. So our mass is going to be rho times the integral. It's going to go from 0 to pi halves. Remember, these are x integrals of our function dx. All right, let's see. Well, we can take the antiderivative of cosine of x pretty easily. So we're going to get rho times sine of x evaluated from 0 to pi halves. Sine of pi halves is 1, so that's rho. Sine of 0 is 0, so we just get rho out of this. So our mass is actually just rho. Kind of interesting. The mass is just the density. So let's find the moment of y, which is going to be rho times the integral from 0 to pi halves. Remember, these are your x's, so it is x, because that's the distance, times the function, cosine of x, dx. So now how do we take the antiderivative of x cosine of x? Well, it's an integration by parts. You can either do it by using the actual integration by parts, setting up your u and your dv, and then taking your antiderivatives, or you can do a tabular in this case, which I believe is much quicker and easier to do. So here is going to be u, here is going to be dv. So u is x, dv is cosine of x. So the derivatives are 1 and 0. Antiderivatives are sine of x, negative cosine of x. Remember, we keep, change, keep as far as the signs are concerned. Multiply, multiply, and then we should be good there. So the moment of y is going to be rho times x sine of x. Change the sign, so plus cosine of x, evaluated from 0 to pi halves. So we're going to get rho times, let's see, if we plug in pi halves, we're going to get pi halves times sine of pi halves, which is 1. So that's pi halves plus cosine of pi halves, which is 0. So we just get pi halves for the first one, minus, plugging in a 0 for x sine x, you get 0. Plugging in 0 for cosine of x, you get 1, so it's minus 1. So it looks like we get rho times pi halves minus 1. That's our moment of y. If we want to find the moment of x, let's do that one in blue. Moment of x is going to be rho integral 0 to pi halves. I always forget I can pull the 1/2 out, but I'll pull it out later. 1/2 f of x squared. So f of x once again was cosine, so it's cosine squared of x dx. All right, so you can rewrite, and you kind of have to in this case, the cosine squared using an identity. So I'm going to pull the 1/2 out to the front. We get 1/2 rho integral from 0 to pi halves. There's an identity for cosine of x, which is cosine squared of x. Cosine squared of x is equivalent to 1/2 1 plus cosine of twice the angle dx. So it looks like I've got another 1/2 that I can pull out to the front. So again, I'm going to highlight that just to make sure. Remember, this is an identity, which is this part. That's the identity. All right, just make sure I highlight that for you. So now I'm going to pull the extra 1/2 out to the front. We get 1/4 rho, 0 to pi halves of 1 plus cosine of 2x dx. Now we can take an antiderivative. So 1/4 rho x. So let's see, the antiderivative of cosine is sine of 2x. Don't forget to multiply by the extra 1/2, which is the shortcut to doing the entire u substitution process, from 0 to pi halves. Let's plug that in. We get 1/4 rho. Let's see, we're going to get pi halves plus sine of pi, which is 0. So that's just pi halves, minus, plugging in 0, we get 0 for both pieces. So ultimately, it looks like we are going to get pi rho over 8. Or you could have written it as rho pi over 8. Either way. There's your moment of x. Now we're trying to find x bar and y bar, which is just division of each one of those moments by the mass. So x bar is going to be the moment of y divided by the mass. The moment of y, going to go all the way back up, was rho pi halves minus 1 divided by the mass, which I think was just rho in this case. Yep, it was just rho, which is really nice. So that means pi halves minus 1 is x bar. Y bar is the moment of x divided by the mass. Moment of x we just found to be pi rho divided by 8 divided by the mass, which is rho. So the rho's are going to cancel out, which is just going to give us pi eighths. So after all that, our x bar, y bar is pi halves minus 1 pi eighths. There we go. All right, we got one more to do. Okay, and this one is kind of important. I am probably not going to finish the entire thing. We're just probably going to set this one up just because time is already at 18 minutes. So what we've got is find the centroid if the surface is bounded by y equals x and y equals x squared. So our surface is bounded by the equation y equals x. Whoops, I totally missed that one. Let's try that again. That's better. Y equals x and y equals x squared. Yeah, something like that. Well, let's see here. One of the rectangles of the given areas, we're going to have to do that using midpoints. So what do I mean by that? So we can basically, remember what we're trying to do is we're trying to take the distances here and find approximating rectangles in between. We're going to do that for an infinite number of rectangles. I had to make it a little bit bigger so you could see it. But this dot right here, whatever that dot is going to be the center of mass in that approximating rectangle. So we're actually going to have to do this basically using midpoints. Let's actually label this, by the way, because that's at 1. That's where those two things intersect, at 0 and 1. All right, so best way to kind of describe this. One rectangle of area using the midpoints. So kind of the orange dot there, orange dot is the centroid of that rectangle. Is going to be representing the centroid, is the centroid of that rectangle. Rectangle. Learn how to spell it right. But we need all the rectangles that we could do from left to right. So we need all of those centroids. So we need all rectangles. So if you remember from Calc 1, how we would find the area of that specific region is to literally just take the top function minus the bottom function. Take the greater function minus the smaller function. So kind of from Calc 1 or AB or whatever you took, the area is going to be the integral of the top function minus the bottom function. Not extremely mathematical way of saying it, but that's the way most people will probably remember it. So let's find the mass. We know that the mass is rho. Integral is going to go from 0 to 1 of the top function, which was x, minus the bottom function, which was x squared dx. That's not an incredibly difficult integration to do. Again, I'm not going to go through the integration process here. It's not really very difficult to do. The moment of y then is going to be the mass, because again, we're talking about 2 dimensions, excuse me, times the distance, which is x. In terms of our integral, it's going to be rho integral from 0 to 1 of x times the distance, excuse me, x is the distance times the mass, which again is going to be the x minus x squared, because that's our function, dx. And again, you can distribute the x through there. In antiderivatives and evaluating that is very simple to do. The moment with respect to x is going to be the mass times 1/2 of the function squared. Nope, not squared. I apologize. It's not squared because the reason that you get the squared is because the mass has the function in it. 1/2 of the mass. Sorry, mass times 1/2 the function. Which again, if we put that into an integral, will be rho integral from 0 to 1 of 1/2. Okay, so now this one this one's going to be interesting. It's going to be x minus x squared. That is the difference between the two. But if I want to find 1/2 of or should I say the average of the two functions for this part, this f of x part right there, that's going to be over here. Well, if you want to find half of these two functions, you really need to take the two functions, add them together, and then you end up dividing them by 2. So taking the two functions and adding them together is going to give you x plus x squared, which is why I couldn't write f of x quantity squared, because in this case, since I'm actually taking two different functions, if I want to find that center of those two functions, I need to take the two functions, add them together, and then divide by 2, which is different than the mass of the function, which is the difference between the two. I know it's a little confusing. If it doesn't make any sense, then you can always just memorize that, but that's what you're actually doing in a case like this. So if you have something in between two functions where one of them is not the x or y axis, then this is the way you're going to have to do it. The nice part about that is these two things are conjugates. So when you actually go to FOIL that stuff out, because that's what you're going to need to do, you're just going to get the first times the first and the last times the last with the difference in between. Makes it quite a bit easier. So the math there actually ends up being quite simple to do as far as the integration. So in general, and I'll kind of write this out so you can see it. In general, the moment of y is going to be rho times the integral of x times f minus g dx. The moment of x, however, is going to be rho times integral of 1/2, and because of the conjugate part, it's going to be f squared minus g squared dx. And again, that's if you have two different functions that are not the x and y axis. If you have one that's where you've got the x or y axis, you'll see that this ends up being like, for example, in the second part here, if g is the the x axis, well, it's just the function y equals 0. So you'd still get f squared out of it. But since it's not the x axis or y equals 0, that's why you get f squared minus g squared out of it. All right, but again, I am not going to complete the integration on this one. You could certainly do that on your own if you wanted to check. I don't even have the answers written down, but there you go. So that is the completion of 15.5a.